Thanks so much. And thanks everyone. Today, I actually have 2 talks in the PyTorch conference. So in the first talk, I got more covering our optimization for the somewhat we call the agentic RL. Yeah, just like Sky RL team has introduced. That's pretty fantastic. So I got to cover today 2 topics on the agentic RL. Yeah, and the remaining session, if you have the ticket to the main session, please come to see my talk and the main conference also. Yeah, thanks so much. And I'm Chenyang from the SGLang team. So in that session, we want to share our experience, how we are optimizing this large-scale RL with SGLang. So by talking about large scale, most of the time we're actually talking about the words like the multi-turn, like the MOE, like the large language model, like these kinds of gigantic models with 100 billion parameters, right? These are the frontier questions we are facing, right? Okay, so let me first do a quick survey, right? So everyone is talking about RL every day. So how many of you guys have successfully running your RL tasks, maybe in your company, in your academia workshop, or in whatever things, or just running up an example? Yeah. Okay, and the second topic, or the second question, have you guys heard about the words like important sampling, or the fashion words, training inference mismatch, or whatever kinds of important sampling? Yeah. The third question, have you guys tried to customize your reward function or your rollout function, the way how you define your sampling, your interaction with the environment? And the last thing, if you have done any kinds of these things, you possibly 100% will hit the wall of performance. And have any of you guys tried to profile your RL and found a way to improve your efficiency? Yeah. If you are an expert, you must have done all of this, and I'm so proud of you. Yeah, you are the expert. I should learn from you. But if you haven't done a bunch of this, and I hope my talk can cover a lot of ideas to you guys. Okay, so we're gonna have several contents of this talk. I will first introduce how we can incorporate SGLang with your own RL library or framework. And the second thing is the partial rolling outs. It's a specialized technique we use for the multi-turn rolling outs. Yeah, and the third thing, important sampling for training inference mismatch is kind of fashion words, and everyone is talking about every day in academia. And I got break down what is it and how we are using something to fix it. Okay, so let's get it started. The first thing is a quick advertisement, right? Why I'm advocating for you guys to using SGLang for your RL. So we think, let's look at some current SOTA RL frameworks. Yeah, this kind of thing seems a bunch of nodes and connections. Yeah, and also there's another bunch of nodes and connections. This kind of thing seems really, somehow speaking, sophisticated or whatever, yeah. But if you break down your RL work, RL is quite like a 5-step. The first step is rolling outs or doing the sampling. In the specific speaking of agents, it is like how your agent is interacting with the environment. You are using the tools, you're interacting with the user to give more specialization of their request or whatever thing. So that's the rolling outs. And the second thing is evaluation. By evaluation, I mean they are calculating the value, the reward or the KL divergence, whatever thing used for guess the loose. And the third thing is the storage. We detach it from the training pipeline to say, in the agent's RL, storage is quite interesting topic. It is like, if you're just doing a single turn RL, the sampling is rather quicker, so you do not need to consider that the sampled trajectories should be stored. But for agents RL, the sampling is in loads of various ways. So we specifically mentioned that there's a storage layer that it will cache the already sampled trajectories into that storage. And you can think about any kinds of ways to reuse these trajectories or do in-analyze. So the fourth thing is the training, right? Using Longshore, Megatron, Torch Titan, or FSDP to train the model and get the fine-tuned model weights. And the final thing is the refit. Yeah, here I'm using the terminology refit, though it seems quite not fashion, but I think it's the most accurate way, it's the most accurate words. If you are using the words like the update weights, right? The training is also kind of updated ways. But by refit, we are specifically mentioned that the model is being fine-tuned, and you should broadcast the trained model parameter back to the inference engine, since we are doing on-policy and online training. If you are not using the latest policy, yeah, it breaks the assumption, okay? So with these kinds of 5 steps in mind, so yeah, taking back to this kind of picture, everything seems much more clear, okay? Yeah, so let's go. And why we are advocating SGLang for an RL life cycle? So the chief thing we want to share is that we think SGLang is a flexible library rather than a rigid framework. By library, we think we can provide any kinds of thing for the users to call. Like if you want to have a right, if you want to have a tool call, we have tool call API, and you want to using Cloud API, Open API, we also have this. Yeah, and another, we provide any kinds of flexible APIs for you to manipulate your KV cache. Like if you want to flush it, if you want to keep if you want to offload your KV cache onto the disk. There's so many things in your imagination, and we all have implemented that. Okay, and the thing that we want SGLang to be elegant, lightweighted, and easy to launch. So that's the idea we want to take to the code community. We want SGLang to be part of the library to backbone your strong RL frameworks, but we do not want to add any requirements or the assumptions to your RL training. So, and specifically speaking, I give 5 reasons for SGLang's utilization in the RL framework. The first thing is open-to-use refit functionality. Just as I said, how can we dynamically and efficiently send the trained model weights back to SGLang? We have 3 methodologies for this, and you can go to our API for reference. And the second thing is the easy to postpone generation. Just as I said, in multi-turn RL, the sampling is rather complicated. So a bunch of times we need to stop some of the sampling right now. So we have these kinds of easy to stop rolling outs for you to use. And also a fine-grained engine sleep and wake up is specifically utilized when you try to collocate your training and inference on the same API. Yeah, okay. And the fourth thing is the training serving alignment. Yeah, this is what we said for example, this PowerPoint is made by the Gamma team, right? The Gamma team, from my understanding, they are more or less using SGLang for their online serving for the AI-powered PPT generation. So if your company is using SGLang to serve your model, it's a rather better way for you to train it with SGLang and then serve it with SGLang. Then you can want to make sure that the model you train is the model you are serving to the customer, right? And the thing is load balancing router. Okay, I can also say it like, given the complexity of the sampling, if you have 100 requests that you want to get the whole rolling out results, that you have loads of ways to sample it, right? For example, you can use a for loop that sends it one by one to different working engines. But as each individual request have diverse sampling trajectories, so we're advocating that users to use SGLang's router that gives you a unified entrance to all the SGLang engine and provides you with the best throughput. So compared with with frameworks that using the the least sliding routing algorithms, we advocating load balancing router that gives better sampling speed for the multi-turn sampling. Okay, yeah, let's go into the first technique part. The partial rolling outs in a multi-turn RL. Yeah, so what is multi-turn RL? Yeah, everyone has no idea from SkyRL's talk, so I won't go into it anymore. But as we said, multi-turn RL is complicated. Imagine that if you are chatting with your deep research agent, it may connect to the tool for a bunch of times. And in this sense, if you want to debug with this agent, right, you should at least record each turn what kinds of tool it's called, and what kinds of requests, what kinds of the response the tool returned to you, and a bunch of things. So given this example, try to debug a multi-turn training system, even just we want to debug the sampling or the rolling outs, is really, really complicated. So that's the difficulty of the multi-turn training. The first thing is that with the interaction, the interacting with the environment takes a long time. You cannot predict that how long a time the environment will return you the response. So this somehow this introduce a complexity of the non-balancing of the request. So that makes the long tail effect. And later I'll give you a picture to demonstrating what kinds of long tail we found out. And the second thing is hard to profile. Just using weight and bias API to see the training loss, the KL diverge, this kind of thing cannot tell you is your training is actually healthy right now, right? If you do not take inside your trajectories, how could you know that your agent works as you expected? If you do not see these kinds of return response, I do not think there's better ways for debugging with multi-thread I/O systems. Okay, so we want to answer the second question first. How can we get a gradual insights? I mean, how can we actually debug in this kind of multi-thread systems? The idea is really simple. Just print it. Yeah, here we have a function called log. It is like you are logging your events into your disk. But the idea behind it isn't trivial, since a lot of time I/O frameworks, they are using Ray. So Ray is trying to concatenating a bunch of print stuffs into one sequence. So if you just want to monitoring one of these kinds of sequence, but there maybe prints hundreds of sequences at the same time, it's really hard for you to find it out. So we're advocating that using the logging and just try to log each of the events into your disk and using offline analyze to try to see what's happening behind your agents. Okay, so that's the idea how we get gradual insights. And with these insights, we can see what we found. There's two pictures I want to show. The first picture is the CDF of the request return time. So it is not so clear, so I can directly point to you guys that we found that on each single worker, 80% of the requests just returns at the first 50% of time. So that means there's 20% of the requests trying to make your training rather longer. Okay. And the second picture is the barrier time. Just as I mentioned, if we pre-allocate all the requests to each worker, one finished worker cannot get occupied to the unfinished worker's request. This is an assumption. So this makes that there will be a specific worker that slows down the whole process. You can see in the centric, there's a blue line, right? That means this is the slowest worker. All the other workers is weighted in the yellow lines to wait for the longest worker to get finished. Okay, so that's the two things we want to get everyone in mind, that 80% of the requests will be finished in the first 50% of time. And there will be a specific worker that slows down the whole process for another total time. Okay, so that's the two insight we get. With this, this is another picture to demonstrating the long tail effect, but it's quite the same. So with this kind of thing in mind, we can think about something like, could we do an oversampling strategy? It is like, if 80% of the requests just returns in the first 50% of the time, could we first sending out more requests than we expected? Say we want 100 requests, we send it from 150, and then until the first 100 coming back, we just postpone all the left 50 requests. So in this sense, the sampling will be rather quicker, right? Just as said, we are doing an oversampling. We send more requests to the engine than we expected, and we get it, and we get the expectation in a rather quicker time. So what can we do for the left postponed one? And the same thing, as I said, we have 150 requests sending off. 100 requests have already coming back, and there's 50 requests still waiting. How can we deal with these kind of 50 ones? Chiefly, we have several things. The most naive idea is we are just through it. We do not take it anymore. So in this sense, it's the most naive implementation, and it turns out to be really effective. But the thing that maybe you are wasting some of these kinds of long rolling outs, right? And another optimization we can do is the partial rolling outs. And it's just like when we postpone this kind of request, we just store it in the cache. In the next rolling out turn, we take the cache first, and we first rolling out the cache first rolling out these things in the cache, and then we adding more requests. And that's the idea of partial rolling out or one step of policy. So the chief idea is that we are doing oversampling, and we postpone at some specific points, and then in the later generation, maybe we first rolling out this kind of left thing. So we also have a paper we call the April, yeah, April that we publish for these kinds of active partial rolling outs. Yeah, so this is how April works. Just as I said, in the traditional sequential ways, you should wait for all the sequence to finish and then do the training or whatever thing. But in April, until some specific point, we postpone the generation and we store the unfinished one in the cache and we do it in the turn. Yeah. Turns out that April could effectively speed up our training for 40% of time. Yeah, though this is done in a small language model, but we're still advocating for these kinds of ideas. And also, we want to mention the partial rolling out is also be introduced by the Kimi I think it's K1.5 paper. Yeah, and thanks so much for their contribution. Okay. Yeah, the later thing is the important sampling. So just as I said, in the agents training, the sampling is really quick. And another difficulty we face for the sampling is that in the sampling, there's several tokens that is really in a low probability. You can imagine that for the agents, for the language model to generate a specific token called token, right? This token should be really in a small probability in the actual vocabulary. In other words, if the agent generates, you cannot using the term like I am you, this kind of term to be the token of the true call, right? So the token for the true calling should be low probability tokens. And these kinds of low probability tokens is actually causing a bunch of troubles for the training side. I found a specific interesting thing is that the training inference mismatch. What is training inference mismatch? The definition is simple. For given a token, we're using the inference engine to guess its log probability, and we also use the training engine to get log probability. You will find out that there's kind of difference that we cannot avoid, and they are quite large. And for these kinds of small probability tokens, the difference even gets worse, right? So if you have a token like the gamma blah, 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 like you have the gamma slash for the true call, we found that the gamma slash for SGLang is really different from that of Megatron. So that caused the problem. In some extreme situation, the probability for token in SGLang should be completely different from that in Megatron. In Megatron, maybe the sampling probability is 0, but in SGLang, sampling probability is 1. So that means the token you sampled from SGLang isn't what Megatron expected. In the RL scenario, it's the off policy. You are using a different policy to do the sampling. You are not using the actual model that is learning to do the sampling. So that's where problem rooted. Okay. So and we gradually found out that a lot of these kinds of training cases are failed due to these kinds of mismatch, especially in the multi-turn training. So what kind of thing we have for the mitigation? Or in the other way, how can we find out the reason why this happens? So there we list several assumptions. Oh, sorry, this is not an assumption. This is the actual thing happens. So we found that everyone knows that the float point adding is not associative. A plus B is not always equals to B plus A in float point adding, right? So considering that in the parallelism strategies, you have different or reduced algorithms. Maybe you have 4 GPUs running together, and you first reduce GPU 1 and GPU 2, and then GPU 3 and GPU 4, and then adding them up. It is quite different, like you first reduce GPU 1, GPU 3, then GPU 2, GPU 4, right? So due to these kinds of slightly different layer by layer, and it's accumulated into the final results, that's the log probability is not accurate. It's not aligned in the training and inference. And of course, Megatron and SGLang, they are using different kernels. This also introduced the non-alignment with SGLang and Megatron. So how can we do the mitigation? I mean, after getting the results, what kinds of things we can do to mitigate this? The first, we think about system methodologies. And let's say if they are using different kernels, why cannot we use the same kernels? And in other words, if the reduced order matters why cannot we introduce these kinds of reduced invariant kernels? Or in other words, it's a fashion word called the bash invariant kernel introduced by the Thinking Machine Lab. So with these kernels implemented, we can make sure that on the inference side, the results is deterministic. That means given the same result to SGLang, it will provide you with the same log probability. It is rather better than previously. SGLang itself is non-stable. Give the same results, it may not give you always the same give the same request, it may not give you always the same results. And yeah, so with this kind of bash environment kernel, we can make SGLang's log probability stable. But that's not the end. So as I said, training and inference, they are mismatched. But with the mismatch, the non-deterministic is one of the problems. But right now, we can fix SGLang's log probability. And Maxwell's log probability is still fixed. But even for this kind of two fixed log probability, they're still not the same. So there's still a long way to go that to make them aligned. Well, right now, we have this kind of thing, deterministic. That means it is rather better for you to debug. If once at a time you found your IO training crash due to illegal memory access, for the next time you want to launch the same job and with the deterministic IO turning on, you can always get the same failure and the same points. So that's the deterministic kernel made for. It haven't finished the final points of the training inference mismatch. So yeah, that's the thing happening right now. Okay. Another way to solve the training inference mismatch is from the algorithm side. So if we admit that a training inference mismatch is always have, how can we do it? So this is the traditional IO methodology called importance sampling. It's the usual way that IO people use to mitigate the off-policy problems. The idea is quite simple. If you're using SGLang to do the sampling, you're just using SGLang be divided by the actual learner. It is like the pi Megatron divides pi SGLang. So that's the mitigation. Okay. It looks rather, yeah, it seems quite different from the system work, right? On the same system work, you have to create new kernels, thousands of lines. But on the algorithm side, just a single, maybe it's a single mitigation could fix a bunch of this, okay? So that's a good point happening right now. This is recent research coming from UCSD and also from ByteDance. They are advocating for the importance sampling to mitigate the training inference mismatch. And they also introduced the new algorithm like the TIS, like the truncated importance sampling, and MIS. We call it masked importance sampling. So that's the idea right now. We also incorporate these kinds of importance sampling methodologies onto our frontier RL frameworks. So we introduced the token level, sequence level, and geometry level importance sampling. And right now we prove it's really in a good condition. Okay. The one final words I want to say about our ongoing project is that we found out the importance sampling on FP8 training is quite out of our expectation. It's really amazing. Okay, so the point is that we found that if you turning on an FP8 mode for the Megatron using FP8 forwarding and FP8 backwarding, for FSDP it's also the same. So just comparing BF16 with your FP8, we found that FP8 is always worse for the accuracy. But turning this kind of importance sampling on, we found that it can grab the FP8 training back. Yeah, it's giving you a better performance or whatever, and with better speed. So yeah, hope we can have this work published maybe in the future. We try to using importance sampling to mitigate FP8 training. Okay, yeah, that's the second part for the training inference mismatch. And right now I still have maybe 6 minutes to go. Yeah, so we can still go over some interesting topics. Okay, but in this point, are there any questions regarding these two parts? First is the partial rolling outs and the training inference mismatch. Yeah, a lot of times I'm speaking to tell you what it is and how we are using simple ideas to solve it. But behind this, we have solid works. And thanks so much to my amazing teammates. Okay, are there any questions for these two parts? Oh, okay, no, thanks. Are there any questions? Okay.
I search on ChatGPT, but I don't quite understand what it means here by community and semantic in the mismatch.
Oh, sorry. I think it's my it's my bad. So, as I said, training and inference, they are mismatched. So you can imagine that then this is the point standing for SGLang, and this is point maybe standing for FSDP. Since this is PyTorch conference, we use FSDP. Okay. So. The best thing is that we found that not only is mismatched, they are also non-stable. If you give the same result for SGLang, SGLang is non-stable, is maybe boundary, blah, 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 right? And you give the same request to FSDP. FSDP is also non-deterministic. So you can see that these 2 points, they are not aligned, and they are also boundary. So the thing we have done right now is that we fix these 2 points. Yeah, they give the same results. It can give the same request. They can give you the same results, but it's still mismatched. So we fix maybe 50% of the problem, but the left parts, the mismatch, haven't been fixed. We just fixed the non-deterministic. Is that clear? Okay. Thanks. I still have 4 minutes to go. So, yeah. So sharing an interesting part, how we are designing RL systems. Thinking about RL systems, you have sampling and you have training. So you have SGLang and you have FSDP running. How could you place these 2 guys? Could you set it always on the same GPU? It is not, right? Because SGLang wants to get all the GPU as its KV cache. So you cannot fit them on the same GPU, right? So the most ideal cannot be implemented. So what we have, the first assumption is that could we do a offloading or the queue and relaunch? Just in the second picture I showed, when we are doing sampling, we launch SGLang and it's finished, we queue it. Then we launch FSDP and then we queue it after it's finished. It can also work. Yeah, in my undergrad years, I used this kind of thing to do the RL training. Just queue it and relaunch it. But yeah, as we expected, queue and relaunch takes a rather longer time. So what is actually taking the time? We're finding out that most of the times to relaunch SGLang is spent on recapturing the CUDA graph. So what is a CUDA graph? In one brief idea is that CUDA graph is a way that GPU is remembering the data flow direction from which address to which address, from which virtual address to another virtual address. So if you keep the virtual address stable, your CUDA graph can still work. But if you change any of the virtual address, your CUDA graph is broken. So we found out that 2 things. First, CUDA graph takes a long time in the queue and relaunch, or the offloading and uploading. And the second, the centric to keep CUDA graph alive is the virtual memory. So that's the idea we have. We call it CUDA graph aware with weight offloading. The idea is simple. When we are doing the weight offloading of the FSDP, of SGLang, we can offload everything except for the CUDA graph. And we want to make sure the next time SGLang relaunch these kinds of offloaded parts, the virtual memory address is still the same. You can destroy the tensor, but make sure the virtual memory address is not affected. So that's the idea behind this point. We call it CUDA memory aware, and we have a framework, we have a library called the Torch Memory Saver. It creates a region for you to protect the virtual memory address. And when you wake up the tensor back, the virtual memory address is still the same. So your CUDA graphs can still be utilized. So with these kinds of virtual memory protected, the CUDA graph aware wake up, we can have these kinds of things right now, right? Every time we just offload SGLang's KV cache and the serving model parameter, and we do the training. And then in the refitting part, we have to load the SGLang back and get the trained model still here, and we do the refitting. And after that, we offload the training model and then do the sampling, right? The picture is quite elegant and ideal. So what's left for this? As I demonstrated here, the red part cannot be utilized. So what's the reason why the red part cannot be utilized? Just as I mentioned, if we expand the KV cache inside this kind of red part, the virtual memory address of this kind of KV cache will be changed. So that means your CUDA graph will be broken. So as long as we want to keep the KV cache alive, we could not expand the size of KV cache. So that's our stage 1 optimization. We make it CUDA graph aware, but we cannot fully utilize the GPU. And in practical, in this point, over 50% of the GPU is being wasted. Yeah, it's quite a big waste for the rollouts. So what's next? We propose for multi-stage memory wake up. So the point behind this is that in the first stage, we have to wake up the serving model parameter and the KV cache at the same time. So in the peak time of the whole life cycle, there's the training model from FSDP, KV cache of SGLang, and serving model from SGLang. And after our new optimization, we can simply waking up the serving model alone, and then in the refeeding time, we refeed the training model to the serving model back. Right, and then we offload the training model, and then we wake up the KV cache again. So in this sense, KV cache will never be expanded, and it can fully utilize all the GPUs we have. Right, so that's the optimization journey we have. First, we found out what is making the offloading and uploading slow. It's the CUDA graph capturing. So we want to keep the CUDA graph always alive, and keep it always alive should make us remember the virtual memory address. And next thing is that if we wake up the serving model and KV cache at the same time, the peak memory cannot allow us to let the KV cache expand to take the left parts. So we wake up it one by one, and then we have this right now. So we have priority in the collocated placement. The GPU memory will be fully utilized just as you are using SGLang itself. Okay, it's quite amazing. Yeah. Thanks so much for our efforts from our member in XAI. At that time, it's in LinkedIn. Okay, and the final points we want to share about this. Oh, I'm all the time, but just one final words. Okay, that with FSDP, you can. With FSDP for the training, you can using SGLang with nearly all the GPU memories. But with Megatron, we found that SGLang can the memory SGLang can take is less than FSDP, because we found that FSDP is rather better to do a fully offloading. The left part the left part on the GPU is less than Megatron. So that's a good thing for FSDP. Yeah. So one sentence takeaway is that with FSDP and SGLang placed on the same GPU, you can using multi-stage memory wake up to fully empower FSDP and SGLang. Yeah. That's the final words. Thanks so much. Okay.